I love that cat. He's focused on the door, right? And there's no lid to his little travel box. And it says, if you focus on the problem, you might miss the solution. Yeah. So that was pretty funny. So these are all about solutions. They're not like the alcohol one is actually what we're talking about today. The solution stoichiometry. So we're going to add in another conversion factor for our mass action table. So we're doing stoichiometry where we are doing the math associated with chemical reactions. Okay. And so we certainly have the molar mass, and that helps us get out of lab units and into chemical units. But what if I give you so-and-so many mils of a concentrated solution? You don't know how much mass was in that solution. You only know the concentration in terms of moles. So you've got to use that molarity as a conversion factor. That's probably the most common use of molarity as a concentration. So let's talk a little bit about molarity today. So last time we discussed molarity, we did percent by mass, we did percent by volume, we then introduced molarity. And today I'm going to talk about the concept of dilution, and then we're going to use it in a stoichiometry problem. So this is a very common practice, what we're going to do today. So pretend you're in the lab and you're going to make up a potassium dichromate solution, and then you're going to use that solution in reactions in chemistry. Okay. Well, you know, you weigh out a reasonable amount. I mean, this is kind of a lot, but still, you weigh out a reasonable amount, like 3 grams of potassium dichromate, and you don't want to make a bunch of it. You just want to make a small lab sample. And so you get out 1/10 of a liter. So you have a little 0.1 or 100 mil volumetric, and you put in 3 grams and dilute to the mark, and you have 3 grams of potassium dichromate in 0.1 liters of solution. So the question is, what's the concentration? Notice how we're putting the solute in the solvent, or the solute into the solution here. So we have, 3 grams of potassium dichromate, and we dilute to the mark, so we get in 0.1 liters. So that's solution number 1. Let's calculate the molarity. So we go and find the molar mass for potassium dichromate. That's a bit involved because we need 2 potassium masses, 2 chromium masses, and 7 oxygen masses. Add all that together, we get 294.2 grams. Okay, and it's roughly 3/300 divided by 0.1. So we end up with about 0.1 molar potassium dichromate. It's coincidental that that equals the volume. So don't think, oh, all you got to do is write down the volume. That's not what's happening here. So solution 1 can be listed as 0.1 molar potassium dichromate solution. That's pretty concentrated. I mean, that's if we didn't want our reaction to be too vigorous, or if we wanted it to proceed slowly, there's many, many reasons why we would want to dilute this. And so now let's talk about dilution. One of the things that we use for dilution are these things called micropipettes. And so you've seen droppers, like medicine droppers. Well, as you get into more like analytical chemistry, biochemistry, and so on, we use these things called micropipettes. And you can see the tip on there is really tiny. I mean, there's a tiniest little hole in the bottom of that thing. And you can use this to deliver microliters of solution. And so 10 to the minus 6, or 1/1,000,000th of a liter, you can easily deliver with these micropipettes. You have this little plunger here and this little tip down here. And this is what we use in science quite a bit. And so let's take a micropipette and let's pipette from the concentrated solution into a new solution. Let's take 50 microliters and put it in 0.15 liters of solution. So notice the fraction is on top is the solute. It's what we grabbed out of the original and we put it into a new volume. So the denominator is the solution, the top is the solute. We're pulling that out of solution 1. but it doesn't look like it doesn't look like the solute. It looks like a solution on top. And so what we need to do is we need to convert this out of volume and into moles. And we have that number here. This 0.1 is 0.1 moles of dichromate per liter of solution. So this right here is our conversion factor for the next level. So this is, again, moles per liter. So we can get rid of this liter right here and get into moles. So all we need to do is then just multiply that by the molarity. And then we also need to take into account, so this liter of solution 1 goes away. But this piece doesn't go away, this micro. So that's 10 to the minus 6. And so don't forget that or we'll have a big problem on our hands. So we have 50 times 10 to the minus 6 times 0.1 divided by 0.15. And that's all you have to do in your calculator. You don't need a lot of parentheses or anything like that. So you would type in 50, the double E key, minus 6, times 0.1, divide 0.15 equals. You don't need to do all of this, you know, parentheses. And I've even seen people use parentheses and divide by 1. I mean, they're making life hard for themselves and they're making mistakes on the calculator. So a lot of times you want to check the work that we do in class with your calculator to make sure you're using your calculator correctly. So after you put all those numbers in, you end up with 3.3 times 10 to the minus 5 molar potassium dichromate. And so that would be the concentration of solution 2. And this is called dilution. We take a little bit out of solution 1, add more water, and we've got a lower concentration. So let's dilute. And notice it's a lighter color too. That's on purpose. We have a really dark orange solution for the potassium dichromate. And then as you make it more and more dilute, it looks more and more like water. Eventually you could get to such a dilute solution that you couldn't tell the difference between water. And so let's look at the math here, what we've got going on with this dilution. So we calculated a new molarity by essentially dividing the volumes. We had volume 1, volume 2, and then the original concentration. And so this volume 1 was the 50 microliters of the original. Volume 2 was the new volume. And M1 was the original concentration. So M sort of helps you remember that we're dealing with molarities. But sometimes I've seen this with C for concentration. Because this same thing would work with percent by volume too. So if we diluted an alcoholic drink, you could still use this as concentration. So like a distilled spirit at 40% by volume of alcohol and water. If we double that volume, we would half the concentration because you see the new volumes on the denominator. Okay, so this, and then this equation, if we rearrange it, we end up with this equation here, which is common. You'll see this in the book. You'll see this if you've had this in high school, you probably remember the dilution equation is this M1V1 times M2 equals M2V2. The reason that is if you take the molarity times the volume, you end up with moles. And molarity times volume equal to moles. And so all this is saying is that the moles of my solute haven't changed. I've changed the volume, and that changes the concentration, but I still have the same number of moles. Okay, so if you take the number of moles and you put it in a new volume, you calculate the new concentration. That's all it is. Let's do another dilution. So when we do dilution, and then we do a dilution on the dilution, notice it's like a chain. And whenever things are linked up like a chain, we call that serial. And think about batteries. The batteries hooked one to another, head to tail, they're in series. If they're side by side, where the heads are together and the tails are together, then that's parallel. So whenever we're doing this, it's called serial dilutions. We dilute it, and then we take an aliquot or a piece out of that diluted solution and put it in a new one and dilute to the mark, then that's called a series of dilutions or serial dilutions. And so this, I'll go ahead and write that out because it's not cereal like the breakfast cereal, it's cereal like in series. Okay, so serial dilution is when you take that next amount out of the diluted solution. So this going from solution 2 to solution 3, this is what makes it a serial dilution. It's a chain. And so we have now 30 microliters of solution 2, and we dilute that to 0.095 liters of solution. So close to 0.1, but not quite. I just made these numbers up. So this is the way it goes. Okay, so let me see the chat question. 5.5 times 10 to the minus 6. Yeah, Carly, I'm having a hard time understanding your question. Maybe, is it on the previous slide? Why don't you unmute, and that way we can see what's going on. Okay, if you want to interrupt, go ahead and unmute, and then we can go on the slide that you're talking about. But I'll continue on. So we have this 30 microliters. Oh, I see. She was answering another question. So we have this 30 microliters of solution 2 that we then diluted, and that makes solution 3. So what we want to do is then multiply by the molarity of solution 2. So that 3.3 times 10 to the minus 5 moles per liter of solution. And so once again, the liters of solution 2 cancel, but the micro doesn't. So liters of solution 2 is gone away, and we now have moles of dichromate in liters of solution 3, but we have to keep track of that micro, 10 to the minus 6. So I do 30 times 10 to the minus 6 times 3.3 times 10 to the minus 5 divided by 0.095. And so you can look at this and you can say, well, I've got a 10 to the minus 6 times a 10 to the minus 5. That's going to be something like 10 to the minus 11. And then I have 30 times 3 divided by 0.1. So that's going to change the powers of 10 by a couple. And sure enough, I see it's times 10 to the minus 8. So that makes sense. If you do this wrong and you end up with 10 to the 8 or 10 to the 12 with a positive exponent, you know you've divided or multiplied by the wrong thing. And so just kind of always do a gut check on your calculations. These are really small numbers times each other. And so we should end up with a result that's even smaller. Okay, so we have 1.1 times 10 to the minus 8 molar dichromate solution in solution 3. And you see it's even paler. So really strongly colored substance. And so even though this is really dilute, you would see a tint of yellow. And so that's serial dilutions, and it's that simple. You just take the piece that you're bringing in, you dilute to the mark, and you multiply by the original concentration, and you end up with this new concentration. Notice how we can make really dilute solutions very quickly. Just a couple of dilutions, and now we're down to 10 to the minus 8 moles in a liter of solution. A liter of solution, you know, this is close to a liter right here. And I can very carefully make something that has almost, like this is 10 billionth concentration, you know. So 1 times 10 to the minus 8, you know, it's very, very dilute. And it's also very precise. Like I can control this very well and make very dilute solutions. So we can do chemistry on things that are not very concentrated at all using serial dilutions. Okay. That's very important in forensics because you're going to have trace analysis, and those are going to be very small amounts. And so you would want to dilute your standards so that they were down at the concentration range of what you might detect. And so this is how we get down to such dilute solutions in doing our detection techniques.